Hello everyone. So again, welcome back to the latest lecture session. I believe we were looking at a particular example relevant to the surfactant extraction based remediation, right? And in that context, we had a particular NaPl, right? And the scenario was such that you are adding some surfactant to be able to, let's say, dissolve that particular NaPl. And then the relevant question was that, or the scenario that we faced was that, for different volumes of surfactant, let's say, what would be the relevant scenario, let's say, right? So, I believe we already worked out a part of the question, but let us look at the question once again. So, we have a source zone, right, that is given out here, and the bulk density of soil is given, the fraction of the organic matter is given, and relevance is that the relevant NaPl can be adsorbed onto the organic matter in the soil. The porosity of the soil is given, it is contaminated with trichloroethylene, right, and aqueous concentration, aqueous as in the concentration in the relevant water, let's say or the groundwater is 15 milligram per liter. Keep in mind, this is not the solubility law, but let's say it should have been solubility if there was equilibrium, but again we will discuss these aspects later. So again 15 milligrams of the relevant TCE per liter of water. Pure NaPl is believed to be present in 1% of the pore space, and it is to be extracted with a surfactant that has a CMC of 200 milligram per liter. What is this about? As you know, initially when you start putting in the surfactant, let's say, right, most of it will be at the interface, let's say, or it will it as in the surfactant will occupy the interfaces, and after that, as in the point or threshold being the critical micelle concentration, which is the CMC, then you will have formation of the relevant micelle, let's say, right. This micelle obviously, right, this is the micelle. Now here this refers to the dissolved phase, or let us say the relevant surfactant at the interfaces, let us say, and this is the micelle phase, let us say. Both are more or less dissolved, but there is a different phase here, I guess, right. Again, so only after you reach or you add enough surfactant such that you reach the critical micelle concentration will you start forming the micelle, and that is what you have out here. And empirical relationship for KOW or KMW as a function of KOW was available, right, though I do not have it here. So, we were supposed to calculate the minimum surfactant, let us say, or the total surfactant needed to completely dissolve the NaPl, right. So, the mass, total mass initially is present in the groundwater, in the soil, and in the NaPl, right. So, the question more or less asks how much surfactant do I need to add such that all the contaminant in the NaPl will dissolve, let us see. So, where will it dissolve into? It will dissolve into the relevant surfactant. So, this after I add surfactant, what will the scenario be? While the mass will still be the same as the initial mass, right, it will now be in the form of what do we say, dissolved in the groundwater, in the adsorbed onto the soil, and now in the micelle, let us say, it will not be in the NaPl anymore, right, but the total mass is going to be the same, as in we are going to look at the scenario where all the NaPl has dissolved into the relevant micelle, let us say, right, and again there can be equilibrium between or a different equilibrium between the groundwater and soil, but as you are going to see here, we are going to consider a slightly different scenario, let us say, right. So, in this context we went ahead and I believe calculated the total mass that was present initially in the groundwater, the soil, and the NaPl, let us say, right, and that is where we were at. So, obviously as we just discussed, the next stage is that you want to be able to calculate the amount of micelle or the surfactant concentration, right. For that you want to know the amount of micelle that you need to add, let us say, per volume of water or such, let us say, right. So, that is something we are going to do or calculate. How now? By equating this total mass which we calculated earlier to the new particular scenario, let us say, which is that the contaminant is in the phase of groundwater, soil, and micelle, let us say, right. So, let us look at that particular aspect out here. So, another aspect is that we mentioned that the surfactant solution is added at 5 times the total volume. So, this is what we now have, the volume of surfactant is now obviously available, right. And so, the total volume of water will be taken to be both the volume of surfactant and the pore volume that was initially available, let us say, right. So, it is 5.4 into 10 power 5 meter cube, as in keep in mind that you are going to keep pumping this level of surfactant through the system now, right. That is the amount of surfactant and water that is going to be available to let us say dissolve the relevant contaminant, let us say, right. So, that is something to keep in mind. So, obviously as you can see we add considerable amounts of surfactants, right. So, we will move on. So, as we discussed, mass that was present initially is going to be the mass again at the new equilibrium, let us say when we add the relevant or enough amount of the surfactant, let us say, right, because we are not degrading the mass or the contaminant, we are only changing it from one phase to the other. So, let us look at what we have. So, this m naught is what we had earlier, and this is still the mass in the groundwater, mass in the soil, and this, as we looked at earlier, is the mass in the micelle, let us say, right. And this is what we are trying to calculate, and obviously for this we need volume of water. This is what we have here, right, that is something we have. KMW, we have a relationship in terms of the octanol water partitioning coefficient, right, as a function of the octanol water partitioning coefficient. We will now look at that. I believe density, we have that. Concentration is the same as this particular concentration in the relevant water, right, that is how we are going to use this particular aspect. And from that particular and once we put in all these variables or plug in all these variables, we will be able to calculate S micelle, the variable that we are trying to calculate, let us say, right. So, before that I need to calculate KMW. Let us look at what we have. There is an empirical relationship given. Again we just rewrite this particular equation, and this is how, this is the equation that we are trying to solve for, let us say, so that we can get S micelle, right. And how do we solve for KMW? There was a particular empirical relationship given here, right. So, KMW is dependent upon KOW, and we see that we end up with KMW to be 95.4, right. And what is this KMW? Similar to the octanol water partitioning coefficient for the particular compound, this KMW is the partitioning coefficient of the relevant compound between micelle and water, let us see. So, if you have micelle and water, what is the partitioning coefficient or what is the preference of the relevant compound? So, here as you see, let us say you have KMW, which is nothing but let us say the concentration of the compound, which is TC here in the micelle, let us say, phase to the concentration of the compound, which is again TC in water, will be 95:1. So, obviously it strongly prefers to stay in the micelle, let us say, right, or in the micelle phase. That is something we discussed, and that is what we are already aware of. So, with this particular aspect, let us say we need to go further, but one aspect, as I mentioned earlier, was that we had m total equal to 0, and we had it in terms of VW into C and so on, rho B Kp C into, again I guess there is another term I am missing here, right, the partitioning coefficient, I guess, right, I think I have that too. Yes, obviously the volume, right, again we have so on and so forth, but again here we have a concentration. The concentration is, or the concentration variable, that is the concentration of contaminant, which is TCE in the water, let us say, right. So, one aspect here we need to obviously make some assumptions. So, as we mentioned here, based on the relevant data, it seems the solubility, the maximum concentration that TCE can hold or have in or water can hold of TCE, let us say, is 1100 milligram per liter. But keep in mind, initially it was only present at 15 milligram per liter, let us say. This is what we had earlier, right. This was the initial concentration of TCE dissolved in water. But if there was true equilibrium, what concentration would have been present? As in, earlier we had soil, let us say, I am using a very generic what do we say diagram here, and we had water, and we had NaPl, which is the pure compound, let us say, right, NaPl, let us say. So, if true equilibrium had been reached, let us say, then what would be the concentration in water, let us say? It would have been the solubility, let us say, based on solubility, or the maximum concentration of the relevant contaminant that would have been feasible in that relevant phase, which is water. So, but as we but the information that is given says that the concentration in water was only 15 milligram per liter. So, that means there is no equilibrium, or equilibrium has not yet reached between the relevant aqueous phase and the NaPl, let us say, right. So, here now we are faced with a dilemma as to what concentration to choose, let us say, when the new equilibrium is considered, as in now we do not have NaPl anymore, we only have the surfactant. So, to be, let us say, to be on conservative side, let us say, I am going to choose that, I am again going to have the same concentration, let us say, right. Typically that will not be the case, same concentration of 15 milligram per liter, right. So, that is something we are going to have, and based on that particular aspect, I end up calculating this as micelle, but the total surfactant will be the one present in both the critical micelle concentration, because this is how much I need to add before the micelle is formed, and the one in the form of the micelle, let us say, right. So, let us look at what we have out here. So, the total surfactant that I need to add is based on the amount of surfactant that I need to initially add before the micelle is formed, and again the amount of micelle required based on what now, how did we calculate this? We calculate this particular variable based on, let us say, the amount of surfactant need to completely dissolve a particular amount of NaPl, right, for a particular volume of water, let us see, or the surfactant. Based on that we calculate these aspects and we end up with a particular value which is considerably high, almost looks like approaching the density of water. So, that typically tells you that that concentration is way too high. That means typically, let us say, we do not we go for larger volumes of surfactant, let us say. Typically these concentrations of surfactants are not practically feasible, I believe, right. But again, so how would you offset that? You will have more volume of your relevant what do you say, surfactant, let us say, right. Earlier we looked at 5 times, let us say, but typically we will have relatively higher values again, but we will use this particular value to look at the further calculations, right. So, this is what we have, or this is the amount of surfactant that we need to add, let us say, to completely dissolve the relevant what is it now, NaPl, if you are adding the surfactant at 5 times the total volume, let us say, right. That is what we have out here. So, let us look at the next case. So, the part B says that, or asks us, if you add it at a ratio, yet as in the surfactant volume, let us say, is 3 times the total volume, let us say, right. So, what is the case going to be, right. But the issue here is that, let us say, earlier we calculated the relevant scenario, let us say, or analyze the relevant scenario such that we add the surfactant at 5 times the volume, right, and for that particular case we calculated the relevant concentration of micelle, let us say, or the surfactant required such that everything dissolves, let us say. So, in this case, if at the same surfactant concentration you are adding less volume of the surfactant, what is going to happen? So, that would mean that all the NaPl will not dissolve, let us say, right. So, that is something to keep in mind. Earlier we calculated the case such that at a particular volume and at particular concentration all the NaPl would dissolve. So, if I am decreasing the volume but keeping the same surfactant concentration, obviously all the NaPl cannot dissolve into the relevant surfactant, let us say, right. So, that is what we have out here. So, the NaPl would not dissolve, let us say, right, but I believe the case asks for the concentration, let us say, that is in the mobile phase. When we ask about concentration in the mobile phase, it means the concentration both in the water and in the micelle phase. So, this is what we have dividing by the volume of water, and we end up with the concentration of the relevant compound in the mobile phase. Let us say, obviously these are relative terms, let us say, to be around 1000 gram per meter cube, let us say, right, considerably high. As you can see, in water it is 15 gram per meter cube, and in micelle the concentration is remarkably high, let us say, right. Obviously that is as expected, as you know that the KMW value was around 95, let us say, right. Again, here though, if you look at the particular case for M total, let us say, what would it be though? Here we were not asked to calculate the M total, we were only trying to look at, let us say, the concentration of the relevant contaminant in the mobile phase, right. Mobile phase includes both the surfactant and the water, and that is we looked at. But for this particular case, where will the surfactant be, or in what phases? It will be present in groundwater, it will be present in soil, it will still be present in some NaPl form. Why is that? Because all the NaPl would not dissolve, and some of it will also be present in the micelle phase, let us say, right. So, that is something to keep in mind now, right. So, let us move on. So, the next aspect is, I believe, let us say, when we add the relevant surfactant, let us say, at a volume of, or 7 times the total volume, right. So, again we need to look at initial case. As in initial case we added the volume 5 times of the total volume of surfactant was 5 times the total volume, and then for that particular scenario we calculated the relevant surfactant, let us say, that is required to completely dissolve the NaPl. So, now unlike in the case B or part B, we are increasing the volume of surfactant, or we are providing more surfactant, let us say, right. So, what will that lead to? Let us say that will lead to obviously complete dissolution of the NaPl, and also that the concentration of the contaminant in this particular micelle, let us say, will now be lower, let us say. So, let us look at that. Obviously NaPl will not be present, right, that is something we discussed earlier, yes. So, volume of the relevant water was recalculated, let us say, and in the micelle, right, this is what we have from part A. And now as we know, no NaPl will be present, the total mass is out here, right, and this is what we have. This is in the groundwater, soil and in the micelle phase, right. We are going to plug these relevant values in to calculate C, let us say. So, C is 11 milligram per liter, let us say, right. So, that is what we have out here. And the mobile phase, as we looked at or understood earlier, we now have it to be 796 gram per meter cube. In part B, when we had it at, I believe, what was it, volume was 3 times the total volume of surfactant. This particular C mobile was around 1000 gram per meter cube. But now obviously, because you are adding more of your particular surfactant, which is 7 times the total volume compared to 3 times, obviously the concentration, let us say, is going to decrease. And again, keep in mind here that we recalculated for the concentration of the relevant what do we say, contaminant in water, or let us say the in water more or less, yes, because the total volume has changed here, let us say, right. So, that is something to keep in mind, right. So, I guess with that we understand what do we say, what do we say are the levels of surfactant that you need to add, and get an idea about, any approximate idea anyway, the levels of surfactant needed, the concentrations that would typically be in the surfactant, let us say after equilibrium has been reached, and so on and so forth. But obviously, these calculations are for understanding the relevant scenario, let us say, right. As in, you obviously can't pump 5 times the volume of surfactant in one go, right, and you can't typically reach equilibrium immediately, let us say, right. So, you are going to go in phases, let us say, right, and then you are going to have to flood the system to remove this particular surfactant and the relevant contaminant and so on and so forth, let us say, right. So, in this context, let us say we will now move on to look at a particular case study. Again, the choice of the case study is based on its relevance to what we are talking about, and more importantly the data that is available, in the public domain, right. So, let us look at what I have out here. So, we have a surfactant enhanced DNAPL, right. DNAPL, typically that is the worst particular type of contamination that you can have, or contaminant that you can have, the dense non-aqueous phase liquid removal. And again, we are looking at a particular army site, let us say this is now in North Carolina, let us say, again, right. So, again, as I mentioned, if you look at look up this particular information, in the public domain, let us say, you will be easily able to look at the relevant document. So, let us look at who prepared this particular document. So, it is by the Naval Facilities Engineering Service Center, right, and you have the relevant others out here, if not the others, pardon me, the relevant agencies out here. As I mentioned, I am only presenting the data that is already available in the public domain, let us say, right, and these are the relevant institutions, let us say, or organizations that were involved now, right. So, moving on, let us say. So, let us obviously understand what the site is about and so on. So, again, as I said, that is a Marine Corps base, let us say, right, Marine Corps base in North Carolina, and again we have PCE, and as we know, or you should know by now, let us say, it is a chlorinated solvent, let us say, right, a chlorinated hydrocarbon typically used as solvent, and let us say now Warsol also a petroleum distillate, I guess, right. And here we are using surfactant enhanced aquifer remediation, let us say, right. Surfactant enhanced, as in here they used a surfactant, some electrolyte, and also I believe some co-solvent, let us say, right. And let us look at some of these aspects, right. Again, they looked at surfactant enhanced aquifer remediation, right. So, they were looking at more or less pilot scale demonstration between April to August of 1999, and based on this particular pilot scale study, they went ahead, I believe, and looked at larger scale application of this particular surfactant enhanced remediation of the particular site, right. So, but again, due to availability of data, we are looking at this particular aspect, let us say, right. So, let us move on. Object 2 is obviously recovery and recycling of surfactant for re-injection during the surfactant flood. As in here, they are not just injecting, let us say, uncontaminated surfactant all the time. What are they doing? They are injecting a certain amount of surfactant initially and pumping it out, and then let us say treating it, and then recycling this particular treated surfactant, let us say, back into the relevant contaminated aquifer, let us say, to be able to get rid of your DNAPL, right. That is something to keep in mind here. So, let us look at whatever we have. So, again, I believe this is North Carolina, and this is where we are talking about the relevant base, let us say. And here we have looks like quite a few contaminated zones, but here we are looking at only one particular contaminant zone, let us say for this particular pilot scale study, let us say, right, operable unit 15, let us say. There were considerable other, as you can see, lots of quite a few contaminated sites out here, but we are looking at one particular contaminant site within this particular military base, let us say, right. So, let us go through. Again, more or less particular, what do we say, we are looking at it in better detail, but keep in mind again, as is the case with most of our relevant sites, we have, let us say, surface water bodies, right, again surface water bodies, right, and also we have what do we say, ecologically sensitive areas and so on and so forth nearby, right. So, these are relevant aspects to keep in mind. Again, as we mentioned, we are looking at only this particular unit for now, let us say, right. So, let us move ahead. So, what do we understand from this surfactant enhanced aquifer remediation, right? Typically, we are going to inject the relevant surfactant and then remove that, recycle that and then put that back in, right. So, we will look at that. So, we are obviously looking at surfactant injection, right, and typically we are looking at DNAPL, let us say, right. So, we will have to characterize this what do we say, characterize the location of the particular DNAPL or site characterization. So, the DNAPL could have had enough time to already reach the relevant impermeable layer, or if there are other semi impermeable layers, let us say, it could also be deposited out there, let us say, right. So, you see, let us say if this is the DNAPL, let us say, right, this is how it would spread out here. So, they are injecting the surfactant, let us say, at different levels, right. This is the conceptual model, obviously, we will look at the actual case later on, and then they are going to pump the surfactant through this particular DNAPL, and this surfactant is going to dissolve part or most of this DNAPL, and it is then going to be pumped out and then treated, let us say, right, and then the DNAPL will be collected for further treatment, and the separated surfactant, let us say, or recycled surfactant will again be pumped back in, right. So, just a conceptual model out here, right. So, site background, again groundwater contamination, I guess, of the shallow and both the intermediate, of both the shallow and intermediate aquifers. And again, typically when we think of PC, it is from the storage and usage of the dry cleaning solvents, let us say PC and Varsol, let us say, typically PC industrial solvent again. So, here too, let us say they are looking at its usage as a dry cleaning solvent, let us say, right. And due to high PC concentration or very high PC concentrations were found 54 ppm, let us say, in groundwater, that is remarkably high, let us say, right. Again, the solubility seems to be 240 milligram per liter. So, it is if not almost at solubility levels, but you know relatively comparable levels with respect to solubility, let us say, right. That means that the PCE concentration is very high in water, and also let us say an immiscible phase, let us say, that is it is present as DNAPL. Initially that is what was suspected. Why is that? Because the concentration of the PCE was very high, right. That is what we see here, 54 milligram per liter. It is almost comparable to the solubility of the relevant PCE, let us say, which is around 240 or 200 milligram per liter. So, typically that means, let us say, if you are having such a high concentration of a hydrophobic compound in water, that means the pure form of the relevant compound or in its NaPl phase, let us say, is going to be present, right. That is what was suspected, obviously, right. So, then they analyzed the particular site and it was collected to the northwest of a particular building, right. And then here we are looking at saturation of up to 14%. For example, in all our homework questions until now, we looked at, I believe, saturations of 1%, 0.5% or so on with respect to NaPl, right. But here you see that almost 14% saturation with respect to the DNAPL, let us say, looks like was the case, let us say, right. That means a large volume or very high volume of the DNAPL is present out there, right. So, this is a remarkably tricky site to remediate, right, and again it was collected from the lower portions of the shallow aquifer, right. And what else do we have? And free phase DNAPL also collected from several well locations, right. And also Varsol, which is more or less an LNaPl, was detected in the upper portions, obviously because it is LNaPl, right, relatively light non-aqueous phase or less dense non-aqueous phase, it can't what we say permeate through, let us say, if I can use the term. It is present in the upper portions of the aquifer, but not as in the free phase NaPl though, right. It is floating out there above the relevant groundwater, but it is not present as NaPl itself, let us say, right. So, that is something to keep in mind. So, different aspects with respect to the relevant site. So, thickness, 11 feet, that is of the aquifer. To the depth to the impermeable layer is around 18 to 20 feet. So, the aspect to keep in mind is that it is relatively shallow, right, that is something to keep in mind. Depth to water table, let us say again 7 to 9 feet, porosity, right, 0.3. And why is porosity a relevant aspect, let us say, or important aspect, because obviously porosity and again permeability, let us say, I guess, do we have that here, hydraulic conductivity, let us say, right. So, this I guess is a bit of an aspect. Again, we need the system to be relatively more porous, or have higher conductivity or hydraulic conductivity, so that it is easier to pump your surfactant through, right. So, that is something to keep in mind. DNAPL zone vertical thickness in aquifer, right, that is considerably thick DNAPL zone, it is almost 5 feet, right. Area to be remediated as part of this pilot scale, let us say, is around 600 square feet, let us say, right, some generic aspects out here. So, we analyze this particular volatile compounds, let us say, by gas chromatography. So, they looked at gas chromatography with the mass spectrometer, right, and what did they see? That primarily PCE with some Warsol as minor dissolved component, let us say, which is from 2 to 14% by weight, let us say, right, that is a remarkably high concentration, if I may say so. So, actual profile, let us say, what do we have here? We have an injection well, right, that is what we have out here, injection well, and here near this particular impermeable layer, let us say, or semi impermeable layer, we have this particular DNAPL, let us say, right, this is the DNAPL, right. So, in this particular site, though they have some LNAPL above the particular groundwater table, so this is the groundwater level, so they have some particular LNAPL out here, but the primary purpose was not to remove this LNAPL, but not LNAPL, it was not present as a different phase, but it was also that it was also miscible, let us say, with the water, but it was not present as a free phase. What was that? Warsol though, but again the objective was not to remove this particular phase relevant soluble Warsol, but to look at this NAPL, which was the DNAPL, let us say, right. So, we have the injection well, right, and then we have the extraction well out here. The spacing seems to be around 15 feet, and then also they have monitoring locations in between, let us say, right. So, these are the relevant aspects to keep in mind. So, we will look at the plume boundary. So, this was the building that we were talking about, right, building 25, and as you can see, a considerable, what do we see, area is occupied by this particular DNAPL, that is remarkably toxic, let us say, right, and also difficult to remove. So, once you have this particular contaminant, let us say, right, in its non-aqueous phase liquid form, let us say, you are obviously again going to have it in contact with the groundwater. The concentration was relatively high at some locations, which was around 50 or 55 milligram per liter of the PCE, and then groundwater again flows. So, you are going to have transport of the relevant contaminant. So, they were looking at a 2 ppb contour, and you saw that they have a relevant approximate contour out here based on the different concentrations at different locations, I believe, let us say, right. So, PCE concentrations in microgram per liter. So, they came up with a generic contour levels, let us say. So, here around 32,840 ppb, right, different cases obviously, let us say, right. Again, we will not spend way too much time out here, but keep in mind that they had considerable number of monitoring wells, obviously because they need to understand the particular site, let us say, right. So, let us move forth. So, DNAPL zone, right, as we mentioned, located beneath that particular building at a particular depth, right, and also outside, extending or protruding outside the area of the particular building, occurs immediately above and within a relatively low permeability layer of silty sediments. The key is that it seems it occurs above a relatively impermeable layer, let us say, right, that is something to keep in mind. So, this is what they actually end up with, as in they had 3 injection wells or row of injection wells flanked by 2 rows of extraction wells and then 2 rows of monitoring wells, let us say, and also they were trying to maintain some level of hydraulic contour, control, let us say, and this, as you can see, is the approximate contour for that particular DNAPL, let us say, not the contour, the DNAPL itself, let us say, because this is the building 25, right. So, this is the actual DNAPL, right, that is something to keep in mind. So, let us move on. So, we have hydraulic conductivity of the DNAPL zone, that is relatively important, right. This is based on after treatment more or less. So, it was relatively what now 1.40 feet per day in the upper 3 feet, as in we knew that the DNAPL thickness, let us say, was almost 5 feet, let us say, right. So we had different levels of what do we say hydraulic conductivity for these for in this 5 feet, let us say. Why is that important? So greater the what do we say hydraulic conductivity, the easier it would be, let us say, for the surfactant to pass through and come in contact with your relevant contaminant, let us say, right. So in the upper 3 feet of this 5 feet DNAPL zone, it was a particular value, and as you can see, considerable decrease, let us say almost 5 times, let us say, right, or more than 5 times if I may say so, or almost 5 times in the lower 1 feet. So in this 3 feet of this if this 3 feet of the DNAPL, it was 1.42 feet per day, and in this 1 foot it was 0.28 feet per day, and in the last 1 foot, let us see, it was almost half of that, 0.14 feet per day, right. So compare this particular 1 foot to this particular zone, which is that the hydraulic conductivity is almost 1/10 or 10 times lesser than what it is in the top 3 feet, let us say, right. So as you know, let us say the deeper that this DNAPL permeates into the what do we say relatively less permeable zones, let us say, it is obviously going to get more difficult to be able to remediate the particular site, right. So let us move forth. So DNAPL saturation, in this case, let us say they are looking at 2% of the pore space on average, keep that it is on average, right. Distribution is around 0 to 4%, the earlier case was 14% by weight, and we are just going to look at the schematic here, let us see, right. What do we have here? We have the surfactant injectate. As I mentioned, they were also looking at some electrolytes being added to this particular solution. So they were also maintaining some level of hydraulic control, and then you are injecting the relevant solvent, let us say, which is also surfactant, electrolyte, and some other solvent that they used in this particular case, let us see. Then surfactant is flooded through the aquifer, right, and through the hydraulic control you are going to have the surfactant moving towards the extractors, let us say, right, and then they are extracted through these particular extractors. And where do they go to? They go to a phase separator, let us say, right. In this phase separator, the DNAPL, let us say, is going to a storage or disposal, let us say, right, and the other one, let us say, is again further pre-treated or further treated by pervaporation. We are not going to go into that into detail, let us say. Again you are going to have some other DNAPL coming out here, and then a feed tank, and then again to further treatment. Again the further treatment, you are again going to have some DNAPL, or if not DNAPL, let us say relatively concentrated or dirty surfactant, part of the dirty surfactant again coming back for storage and disposal, and a part of the surfactant or initial fraction of the surfactant will be recovered, and this again will be pumped back in, let us say, right. So here more or less you have 2 stages of treatment for your surfactant, and then a part of it is recovered, let us say, and then that is re-injected here, right. So that is something to keep in mind. So we will look at the relevant aspects only in a bit more detail. So typically pervaporation, let us say, based on the non-porous membrane, let us say, what are we going to have? You are going to have separation of the phase. What are the different phases? They are the NAPL and the surfactant on the mobile phase, if I may say so, or if not the mobile, the surfactant and water. So that is what we are doing out here. So we have the DNAPL here, and also the surfactants and water here, let us see, and again as I mentioned, they are going to further treat it to MUF. Again what is happening out here, let us see, we are again having permeate, which is water, let us see, and some water, surfactant plus water, which with concentrated for re-injection, let us say, right. So this particular concentrated surfactant, let us say, is now going to be re-injected again. So again 2 stages, pervaporation and MUF, right. We are not going to go through that in relatively greater detail, that this is more or less based on the ultrafiltration, let us say, right. MUF is based on ultrafiltration, right. So demonstration approach, let us look at the endpoint. So they want to bring it down to a saturation levels of 0.05%, that is what they are trying to look at. We will just look at the relevant timelines, let us say, for this particular session, and then we will end this particular session for now, and then carry on this particular session in the the relevant aspects in the next session now, right. So timeline, let us say, keep in mind it was only from April to September or such, only a few months within or in the year 1999. Why is that? Because they were only looking at pilot scale demo, let us say, initially, let us say. So they were setting it up 14 days, they were flooding the system with water initially, let us say, right, they were flushing the system, and then they were injecting the relevant surfactant. The key is that initially with this fresh surfactant, and over a period of almost a month or more than a month, let us say, right. So that is something to keep in mind. and then again continued for, let us say, for 38 days, I guess, right. The total you can calculate that, and then surfactant flood with recycled surfactants, as in while you are pumping the surfactant through, we know that by pervaporation and MUF treatment, let us say, the relevant people were again recycling or being able to get back some of the relevant surfactant, and then again the surfactant flood with the recycled surfactant, and that was for a period of 10 days, let us say. An extension of the recycled surfactant flood, as in they kept doing that, let us say, right, and then they flooded the system with water, let us say, right. Why are they flooding the system with water? Obviously, once you pump out the surfactant, if there is any residual surfactant or any other relevant phases, let us say, that are relatively soluble in water, you want to bring them out. So, that is why they are now flooding the system with water here, right. So, that is what you see out here. So, they are flooding the water almost for, let us say, a period of 1 month, and then they are injecting the tracer to look at the relevant flow paths, let us say, and then again flooding the system with water, right, and then treatment completed and water flooding continued till so on during soil sampling. They obviously need to take the soil samples. Why is that? To look at PCA concentration adsorbed onto the relevant soil, as in you do not just want to remove the PCA in the NaPl and also in the aqueous phase, which is the groundwater, you also want to remove the PCE, right, which is adsorbed onto the relevant soil. So, that is what they were trying to do, and then they were then bringing it down. So, I guess within around 4 or 5 months, let us say, right, they were able to complete this particular project for an area of around 55 meter square or 600 square foot, let us say, right. So, again that is more or less a generic overview, right. So, we will continue this in the next session, and thank you.